Good morning. Last week we covered PennyLane, two parts. We covered one is the tutorial from Dr. Sereno's video, and we went through the notebook. Here is the YouTube link if you want to watch his video. And then we covered PennyLane fundamentals. There are four parts. We went through them and discussed this crash course on the basic of PennyLane. Today I'm going to supplement additional material from this introduction island in PennyLane's codebook. So this is the part that we already covered, and there are four small regions. I'm going to take some material from them. And there will be four parts. Let me go to the notebook. I will post the notebook in Brightspace so you can download it. So I call this is some useful tricks, functions that I extracted from the codebook. So first, this is import PennyLane as QML, and then we also import PennyLane's NumPy. Okay, so as I said, there are four parts divided into these titles. Warming up will be the first part. And then I will move on to more material on Euler decompositions to achieve arbitrary one-qubit rotations. And there will be some analytic that we'll work through to get some of the answers. The third part is about measurement. The fourth one is to introduce more multi-qubit gates. Okay, let's get started. So this recorded lecture would not depend too much on the prior PennyLane that we covered. There will be some that you probably have seen, but this will be self-consistent. So our first task is to design a function to simulate a quantum algorithm that does this. And we're not going to use PennyLane's function. We'll just start with using NumPy. First, we'll initialize a qubit in state 0. In terms of vector, this will be a component 1, 0. And we are going to apply the provided unitary operation U. So for example, you see here, if you look closer, this is actually a Hadamard gate. And then this should be 3. We'll simulate measuring the qubit and then output the result 100 times. So in a sense, it's reporting the shots. So first step is to initialize the state, and we're going to represent it as array 1, 0. Then we apply unitary. So unitary really just use the NumPy dot u dot the state, the matrix u dot the state vector 1, 0. Then we're going to measure the qubit. So we're going to output the outcomes. So these would obey the Bohm rule. So P0 is probability of measuring 0, and P1 is probability of getting 1 outcome. So and these are just the coefficient square. And so what you do is you output them using the NumPy function random.choice. So you have choice 2 options, 0 and 1, and you set the probability. It's 0 if you have probability 0, if it's 1, probability P1. And of course, they have to sum up to 1. And this size is number of shots, number of measurement we perform. And you return a list of these 0, 1 outcome. So here is the quantum algorithm in its entirety. So we initialize the state, and then we apply the state. This is the output of the state after applying U. Then we use this function to sample it 100 times. So let's run this cell, and you can see already the result there, but let me run again. So here I'm printing the probability and also return this sequence of measurement outcome. Okay, so here is where I print out the probability. Okay, so an exercise you could probably do now, because you already learned PennyLane basics, is to rewrite the above algorithm, quantum algorithm. This is the simplest using PennyLane function. We cover some of the basics ingredients. For example, you will need a decorator, this QNode device. You need to choose a device, and then you will need to assign the number of shots in the device, and you also need a function to turn U into a gate, and then you would use samples, QML sample. But since I'm going to make this self-contained, and we'll do this exercise later. So first, we're to introduce the QNode idea, because a PennyLane need a QNode to run a circuit in order to return from a quantum device. So the QNode will contain a device and then the circuit itself. So let's first define a circuit. You can see that's here. I got the code, of course, from the codebook, but it's implement a circuit like this. You first do the Rx rotation with angle theta. That's the argument of this function. And we only have 1 qubit, so if no, actually we have 2 qubit because we have 3 qubit actually, because we have CNOT gate. So you can see that it apply Y qubit 1, RZ qubit 2, followed by control NOT 0 to 1, 1 to 2, and 2 back to 0. And return, this is the probability distribution about the qubit 0, 1, 2, all the 3 qubit. For this, you can choose a subset of qubit. So let me just run this. And if I now try to run this function, so this example is I input a 0.1, 0.2, 0.3. It actually does not give you the probability. It just says probs wires equal to 0, 1, 2, basically just say what I wanted here. So it actually does not run. So this is related to what I said earlier. The PennyLane uses QNode to run the circuit. We could actually see what exactly this is, the type of this. Let's see what it's. So this is a PennyLane measurement props dot prop MP. Okay. So let's draw the circuit. It's probably easier to visualize. Rx, Ry, Rz, C0 0 to 1, and C0 1 to 2, and C0 2 to 1. So this is like a periodic for 3 sites. Okay, just remind that you draw this using QML.draw underline MPL, the circuit and an argument. If you don't use the MPL, then that would return a text text generated circuit. So for example, you just use this, sorry, remove this equal sign and correct this. Yeah, so I prefer using MPL to draw the circuit. So how do we run this to get the property? As we already learned before, we will need to define a device. So from QML.device, we'll choose this default.qubit and we'll assign 3 wires. You could assign actually more than 3 as long as you have enough wires, which is fine. So let's call this DEV and let's create a QNode. So this QNode binds the function and the device. So you will use my QNode equal to QML dot capital Q node. And then you can run the above circuit. You can run this my circuit. So let's set up the value, the argument theta phi omega 0.1, 0.2, 0.3 as I have above. Now we can really run it, but you really use this my Q node to run this. So essentially, my Q node it become a function that can run the circuit. So now it return the probability. And since this is 3-qubit and we measure all the 3 qubits, I return the probability distributions. So this is the 0, 0, 0, 0, 0, 1, and etc. up to 1, 1, 1. This is the probability distributions. Okay, so next I want to discuss how we can extract information or specs about a circuit, or maybe more about the QNode. So we'll use qml.spec. If you want, as I said, always you check up the documentations. So I just usually use Google, seems to be easier. So this give you resources of information about a quantum circuit. We didn't introduce this last week, but this is useful. So this transform, okay, converts a QNode into a codebook that provide resource information about the circuit after applying the specified amount of transformation expansion first. Okay. But there is example here. But maybe that's you can also we won't go into this here, but we already have the codes, but I want to explain in slightly more detail using this example. So we have my circuit above, right? This circuit here, the 3-qubit circuit, rotations and CNOT, but we have not made it into a QNode yet. So let's just see if we just blindly apply this, and let's see what you get. So you immediately get an error. You can, of course, you can assign this, but when you print, there's an error because it says function object has no tribute func. This is from here. It's qnode.func. So you need to add a qnode. So in order to do that, we just used my QNode that's defined earlier. Here. It's really binding the circuit and the device. So if we then use this my QNode as argument in the specs, and these 3 arguments are for the QNode. So you can print specs. So you see resources is dictionary, resources that include a lot of information, and there's resources, number wire, gate, etc. and gate size is depth, etc. An error, my observable, etc. It's actually containing information about the circuit and the device. So let's see, for example, let me just first use just print out the specs resources. So give you a number of wire, gate, depth, shots. Shots, there's nothing here because we didn't specify shots. Gate type. So you have R, X, R, Y, R, Z, C naught. It's actually counting the number of these gates for you. So we useful information and gate sizes. So 1-qubit gate have 3, 2-qubit gate you have 3 as well. So this is useful information. So for example, you can if you only want the gate type, you just do the gate type RX. And you may want to okay, suppose I see if I have something else. Holy X. Let's see what it would tell you. This is 0. Okay, maybe relevant information would be the circuit depth. So you can see the circuit depth is 4. This is useful because when you are trying to optimize the circuit, this is probably an important matrix that you want to see. That's lowest as possible. And here's number of shots in the device. And since we have not specified, so therefore it has no shots number. Okay, there's another circuit example with specs. So here we define a 2-qubit device, have 2 wires, and we define the circuit. It have Rx, Ry on the 2-qubit, and then apply the C naught, and then it return the expectation value of Z only at qubit 0. So maybe let's print out a circuit. QML, okay, thick, AX, QML, draw, MPL, circuit, let's say 0.3. And then we also print out the specs. Right. So notice when you want to print out specs, if there are argument, you should also supply the argument. So for example, I use this. This is the circuit, and these are the specs. Let me just illustrate. What if I just say spec and without anything? Then it'll just tell you that this is its type. Okay. So we can extract the resources. The depth is what we want. And we can also the gate type. So we just say specs. Also, this is in the resources. Okay. So you have these X and Y and then C now. This is very useful. Okay. So next, we're actually building up elements that allow us to do these simple quantum algorithm. And as you know, we have these unitary using array and NumPy. And so the next question is, how do you convert that into a gate? Okay, so let's go back to the code here. This function qml.qubit unitary allow you to do that. It can be list upon. So as usual, we define a device has only one wire, and this is the unitary, and you may recognize again this is Hardeman, and apply U. What we will do is use this function and convert this U into a gate and apply to the wire 0. So, and then you return the state. So if we plot this, it will show that this apply this U and measurement because we return the state. If yeah, if you when you are using a circuit and if you return something, it will always show a measurement symbol, regardless of you whether you return the state. In some sense, you didn't measure it, but it still show that. And if you could also use probability, the prop, it will still show the measurement symbol as it should. Here, of course, we didn't define the shot, so we cannot use the sample, but somehow it's not giving you any error. But let's see if we run this, apply U, what we'll get. Then you see the error because there's no shots. Yeah, so it's useful to just play around with the code as you should. And for example, let's just return the state. And now if we return the state, should return a vector. This is actually the plus state, 1 over square root and 1 over square root. Okay. Next, we'll examine this arbitrary 1-qubit gate. This is called QML.rot rotation, right? And there are 3 angles, phi, theta, and omega. And you can see that this is actually can be decomposed into RZ rotation with phi, and then RY rotation with theta, and this RZ rotation with omega. Okay, so let's just define this. This is the decomposed version. Okay, so there is an exercise. Can you verify that the above circuit give the same action as QML dot rotation by giving examples? Of course, you can just analytically compute the multiplication of these 3 matrices to verify that. And how do we use the circuit and examples? So I suggest you pause here to think about it and try to work it out. And I will give you the solutions, example solution after you come back. Okay, so now I'm going to reveal the solution that I have. So here I define device, 1 qubit, and I'm going to check this rotation, 3 angles that's above, phi, theta, omega. And I first apply this decomposed version, okay? And then I apply the inverse of this matrix, this gate, U gate, rotation gate, and apply the adjoint. So this is U dagger. So you can actually invert it by using this QML.adjoint. So we have seen this actually last week, but In case you want to know more, always go to the documentation. Yeah, create the adjoint of an operator or function that apply the adjoint of the provided function. And it's actually you can use QGIT, you can use machine learning technique to do that. Okay, so this is applying the joint of these Rx. Okay, this apply joint also Rx. Okay, it says does not support batching of operator. Okay, but that's not really about that. Come back to our circuit. And we return the probability of measuring that because we start with 0 and we apply the inverse, we should always get 0. So let's try that. So I'm going to get 3 random numbers. I want to see if it's always the same. Always get probably 1, 0. Okay, so I'm going to run this. So I'm going to run this check function. And I'm going to compare the probability whether it's close to 1, 0. So I use this numpy.o close. This is the first item, second item, are they all close? Okay. So this is the random number that I got, and this is the probability distributions. Up to the machine precision is close to this. Can run again. So give you a different set of random number, right? Right. So in general, it may be a hard problem to check whether two circuits are identical because the number of gates will be large, depth may be large. But this is a way to verify the circuit. Okay, so next we just play with these simple gate poly X, poly Y, Hadamard identity. So the text we are given here is to complete the functions such that we apply the rotation U to either 0 or 1 depending on the argument state. So there's a input state depending on it's 0 or 1, then we'll initialize it to 0 and 1 and then apply the unitary U here. Well, this was obtained from the codebook. You could probably use U has U as an argument that you can apply to any U. Okay, so the way that I did it is if the state is 1, then I apply poly X toward 0 because it starts with 0. And if it's 0, then I apply identity. Actually, I do not actually write this, but yeah, because it's initialized in 0 state. And here I add a checking. So I raise value error if it's not 0 nor 1. Okay, afterwards, then I apply this qubit unitary U. So to make it a gate and apply and return the state. Okay, let me first draw this with state 0. And draw the other one with 1. So it has 2 different circuits. And what if I say a state 2? Okay, what's your prediction? What would you get? Let's say there, state 2, then we get error. Value must be 0 or 1. Okay. So sometimes you want to make sure that your program can deal with error. You can check. Otherwise, if you may get something weird. Okay. So the next text is to apply the automat to 0, 1, depending on the argument state. This is very similar to the above. Just change to automat. Okay. So then I try the two example 0 and 1 here. Okay, the next would be RZ. This is rotation. So the first thing that we do here is to use the RZ to reproduce same action as poly Z on the plus state. So remember, poly Z is actually proportional up to a phase to Z rotation around the Z axis by 180 degree. See, I could use this here. Well, I'm just draw the block sphere. So rotation pi is e to the minus I pi over 2 sigma z, and this is cosine pi over 2 infinity minus I sine pi over 2 sigma z, and this is 0, so you get, this is 1, you get minus I sigma z. But the overall phase does not matter. Okay, so this is the answer, of course. They call this fake z. First, we need to apply Adama to make the state into plus, and then you apply the rotation RZ with angle pi and return the state. Okay, let's draw this. Next, we play with these S and T gates and some join. So specifically, we need to implement this circuit. Okay, so it's quite easy. You just literally translate this to the gate. So first is Hadamard, second is S gate, and the third one is T gate, but we can use a T adjoin. So we will need to use a QML that adjoin to take this T into its adjoin. And then it's followed by the RZ with angle 0.3 and followed by the S dagger. So we also use adjoin and return the state. So also draw this. This you could probably print this many rotations. It give you the state, but yeah, this is just some random rotation angles. Doesn't have any specific algorithmic meaning here. Just apply the sequence of gates. Okay, so we're toward the end of the part 1. So remember our first one algorithm in this notebook is it's not really a algorithm. It's really just doing measurement, applying gate, doing measurement. Okay. So how do we implement that? Remember that we call that we we initialize in 0. For circuit, you don't need to do anything. It would already be initialized in 0. And then you apply the U, which is from a unitary, and you measure. Okay. And you output that. Okay, let's get back to where we were. Okay, yeah, I realize we actually have not introduced much about the sample, but this we're going to do it here. So to implement that algorithm, this is U that's given. Maybe I want to actually use that as an argument. U, so I can apply other. So I'm going to use this as argument. U, so I can apply other unitary matrices. So it's literally very simple. You don't need to do anything on initialization. Next, I apply U. This is qubit unitary U, the given unitary, and return sample. But the thing that's different from above, anywhere else that we have seen so far is the device. There's one device up to here the same, but now we input the shot. We give the shot number. Okay, so let's do that. So you see that then this return, we use QNode.sample, and this allow us to do the sampling. Yeah, we would implement the sampling on our own using NumPy's random choice right here between 0 and 1, either 0 or 1. Okay. Yeah. So this is probably the end of the part 1, but maybe one thing we could try to play with is the specs. What is the specs of this? Right, so what is the spec of this function? Let's just copy this. Specs equal to that. Okay, this is toward the end. I think this probably would take half the lecture time, or maybe more if you pause and play with the code. Okay, so this QML spec, quantum algorithm 2, and let's print this specs. Right. So here now we have this, we can see the shots. This is shots number. So let's say specs. That's shots. Okay, first we should give the resources. Right now we have the shots. Okay. I hope you learned something from this part. So we'll give a break and then come back to part 2.